Hi everyone, my name is Thomas Kim. Today is May 30th, 2022. This is 122nd episode for CUDA SQL OpenGL OpenCL MFC tutorial series. In this episode, I will demonstrate generalized partial derivatives and gradients on CUDA GPU device. More specifically, we will solve Advanced Engineering Mathematics 7th edition by Peter B. O'Neill, Chapter 11 for the gradient field. In this book, Advanced Engineering, Peter B. O'Neill, 7th edition, Chapter 11 for the gradient field. In page 357, we will solve this problem numerically. Without further ado, let's get started. Start Visual Studio Code, select SQL OpenGL OpenCL, select folder 122, click this button, partial derivatives.cu, hit enter. Also open adv lambda.cu. We created this file in our previous episode. I will copy up to this point. Copy, paste it here, Ctrl V, Ctrl Home. I will paste a link here. In our previous episode, we learned how to use process lambda, this function. Scroll down. I will delete this part. Also, we created this simple class, three-dimensional vector class, in our previous episode. So, if you haven't watched this video, please watch it, because we created this class in our previous episode, in episode 121. Also, I explained how to use process lambda, this CUDA Kernel Abstraction. Scroll down, void test, partial derivative, and gradient. Into main, I will copy and paste it here. I will copy this text. Advanced Engineering Mathematics 7th edition by Peter B. O'Neill, Chapter 11 for the gradient field, page 357. From this PDF, Chapter 4, the gradient field, page 357, we are going to solve this problem. Copy, paste it here. Please note that I'm using UTF-8 with a BOM encoding. This is x square. Phi is a function of x, y, z defined like this. Its algebraic gradient is this vector. This is x square. This is x square times z, x square times y square. We have to fix like this. This equation from this PDF is actually wrong. If we differentiate p with respect to y, this is incorrect. In this equation, y is missing. I fixed this part. This is original text from this PDF. This is incorrect. It should be fixed like this. Here, O F, we will execute on GPU device, so we need device. Don't miss this keyword. X, Y, Z, semicolon here, return this is our function, semicolon. I will correct like this. We should fix our calculation like this. Here, rho f gradient device rho x, rho y, rho z. Its return type is D3B, three-dimensional vector, semicolon, return. We are differentiating phi with respect to x. TCE derivative adapter. We need to capture f. Copy this. So f equals phi. We pass TCE sequence T 0. This is a type. This is a type. So we create an instance 0.001 f. F is this lambda function. Then x, y, z. This is partial derivative df over dx. This index 0 represents the first parameter or x. So it represents df over dx partial derivative. I will copy this once again. Copy, paste. Now we are doing partial derivative with respect to y, so it should be 1. This represents partial derivative of f with respect to y. Copy, paste. This is partial derivative with respect to z, so it should be 2 dz. Curly brace, semicolon. Now we fix our code like this. The return type D3B or D3B has 3 members. This is the first member, this is the second member, this is the third member of D3B. Now scroll up. In the class D3B, X is the first member, Y is the second member, Z is the third member. Now scroll down. Here, this is the first member, this is the second member, this is the third member of D3B. Now SED vector double XX 1.0, 2.0, 3.0, 4.0 arbitrary number. This is YY, CZ, 2, 3. I'm putting arbitrary number 5, 5, 2, 2. I set arbitrary number for X, Y, Z. Auto estimation TCE process lambda. We will pass this F gradient. This F gradient returns D3B. So we pass return type D3B, then this F gradient, then XX, YY, ZZ as argument. I will define another lambda or exact gradient. It will be executed using CPU or X or Y or Z. It returns D3B semicolon. We return D3B. Now scroll up. This is ith component. Here it should be 2 times x times y times. This is x component. Scroll up. This is y component. Y component. X times cosine times z minus x times x times y times z times sine z. We should fix like this. I will arrange. Now scroll up. This is k term or z component. Paste minus x times y times sine y z. So this is z component. I will arrange like this. SED vector D3B exact values for SED size t I equal 0, I less than xx size plus I exact values in place back. We call this function by passing xx, I, yy, I, zz, I. Now here print estimations, and then print exact values. In the function main, print std precision. I will set 10 decimal points. Now open up your command prompt. We are building partial derivatives.cu nvcc std c++17 o n.exe extended lambda expt relaxed context for xptx as suppress stack size warning partial derivatives.cu. Hit enter. CLS N. I will make it bigger. So estimation exact value. In case of estimation, we used numerical approximation, numerical partial differentiation to evaluate gradient vectors of P, this function. In case of exact values, we used exact gradient. These are algebraic derivatives of this function. So, estimations are our numerical approximation. Exact values are algebraic differentiation. They are exactly the same up to 10 decimal points. Our numerical approximation is accurate up to 10 decimal places. Here, in this expression, 0.001, 0.001, 0.001, what are these numbers? I will paste some links for 5-point stencil algorithm. For information about 00.1, these numbers, please control-click this link, 5-point stencil algorithm. In this document, H are represented 0.001, 0.001, 0.001. I basically use 5-point stencil algorithm, this expression. Please control-click this link.
Really, it helps you.
In this video, I explained how to derive this expression for first-order derivative and second-order derivative and higher-order derivatives.